So I will be presenting on my group's work on the automatic detection of emerging threats to computer networks. I'm going to start us off by giving a presentation of overview of my presentation. So the problem that my group is working on is that of cybercrime, or more specifically network intrusions. We can broadly define a network intrusion as any unlawful or access to a network computer system or its abuse. So in the first section of my presentation, I'll be giving background information on networks, network intrusions. In my second section, I'll be looking at network intrusion detection, and this involves the automated detection of these intrusions and threats as they occur in your networks as a step towards their prevention. And I'll be giving an overview of existing techniques for performing network intrusion detection so as to create context for my own work. And then in the final section, I'll be looking at the research and development work that the CSIR is doing in this area. Okay, moving on to the cybercrime problem. Now, we can define cybercrime as any crime in which a computer is the object of the crime or is used as a tool to commit an offense. Now, cybercrime spans a wide variety of illegal activities. Examples range from fraud and financial crimes to identity theft and theft of classified information. Now, the thing with cybercrime is typically one reads about isolated cases of cybercrime in the media, but one doesn't always get the bigger picture. It's not very well communicated. So one might ask, what is the true extent of cybercrime? And it turns out it is quite big. Cybercrime, a study has actually estimated that cybercrime has a global impact of around $388 billion a year, which makes it bigger than the international drug trade. It's more than 100 times the annual expenditure of UNICEF. So clearly, cybercrime is something that is worthwhile to address. Cybercrime is also not something that is just isolated to other countries. We are very much in the spotlight as well with cybercrime. It's been growing steadily over the last few years. It's been estimated that South African companies lose around 5.8 billion rands, or 0.14% of the GDP, to cybercrime. It's noteworthy that cybercrime is not just targeting South African companies, but that individual users of the internet are also at risk. Around 55% of South Africans experience cybercrime yearly. We have some very specific challenges in the local context as well when it comes to dealing with cybercrime. Our SMMEs typically have very small ICT budgets, so they can't afford to spend a lot of money on cybercrime, and hence it is a big problem. We also have a local skills shortage with very few cybersecurity professionals in the country. And we also in general have a lack of awareness of cybercrime. But it is encouraging to see that over the past few years, several cybersecurity awareness campaigns have been launched to address this issue. Now, cybercrime frequently involves the illegitimate access to network computer systems or their abuse. And it is this subset of cybercrime that my group is concerned about. Now, it turns out that our network computer systems are quite vulnerable, and this is often due to a security administrator not applying security mechanisms correctly in a network. And as an example, we have passwords. Passwords is an access control mechanism. But if the administrator allows the users to choose weak passwords, it's quite easy for a hacker or an attacker to actually guess these passwords and gain access to the network. So there is a big vulnerability in our networks in this regard. Mobile devices is another example. Many companies allow their employees to bring their mobile devices to work and to plug in these devices at their workstations. And the problem here is that some of these devices might have malware or viruses contained on them. And this is an opportunity for the virus or the malware then to spread throughout the network. This is also another vulnerability. We also have outdated software and misconfiguration of hardware. Outdated software is a big concern. Software packages oftentimes contain flaws which can become security vulnerabilities because an attacker can potentially exploit these flaws in the software. And the idea with updating your software is to actually remove these flaws to close the door for the attacker. But this frequently does not happen. People just don't care to update their software. Also, another vulnerability is unencrypted transmission of information. It's quite easy for somebody to eavesdrop on a network, in some cases, of course, and in this way gain access to confidential information. So this is a list of flaws that exist in our network, and conventional security mechanisms are typically not used correctly in order to stop them. So on top of this as well, you have what you call emerging threats or previously unobserved attacks. And what this involves is an attacker actually learning how to exploit or discovering a new flaw in some software or hardware system that the security community is not aware of. And this has grave consequences because this person can then exploit this vulnerability without security administrators knowing how to counter it or maybe even being aware of this threat. And it's been shown that these type of emerging threats propagate quite rapidly through networks and that people typically have a slow reaction time to them. So this is, of course, also a big concern for our networks. So having painted perhaps a bit of a bleak picture of the current state of cybersecurity and cybercrime, I'll now move on to network intrusion detection. So network intrusion detection, I defined previously, basically what it involves is it involves the automatic detection of intrusions or threats in computer networks. And we want to use network intrusion detection as an additional security layer in our networks because of these vulnerabilities I've shown previously. Now, why do we want to do this? Well, the answer is that if we're able to detect intrusions in their early phases, so as they start happening, we can potentially block these attacks from being carried out successfully. So typically your intrusions or attacks occur in several phases, and I've indicated some of the phases of a typical attack here in the diagram. Typically in your first phase, the attacker is looking for a host that he or she can attack or exploit. In the second phase, this person gains access to this host by exploiting some vulnerability in the system. Thereafter, the person tries to take control of the node or of the server by doing something like escalation of privilege, for instance. And then finally, this person, having now control over this node, can actually download information from it or modify information. So the reason I give this breakdown of an attack here is to illustrate the concept that if we are able to detect an intrusion early enough, maybe in the first two phases, we can potentially block that intrusion from causing significant damage. So detection is a first step towards prevention of intrusions. So over the past 10 years or so, engineers and scientists have developed technology for performing intrusion detection. We call this technology network intrusion detection systems. These are hardware or software systems that carry out the functionality of detecting intrusions in your networks. Hardware devices are more popular nowadays. One can connect these hardware devices to a spanning port of your router or a switch, or in some cases even place it in between your external network and your router. These configurations have different advantages and disadvantages, of course. And there's also a tendency these days to actually incorporate intrusion detection functionality into the devices themselves, the switching devices and the routers. And I've given two pictures here of devices which do this. So at least there is some response in that people are developing technology for this, but the problem is far from being solved. So in intrusion detection, there are two main types of detection approaches. One gets misuse detection and the other is anomaly detection. And these are quite complementary in the protection that they provide. Misuse detection is very much like your antivirus software. Your system has a set of predefined signatures of known malicious traffic patterns or intrusions. It's almost like you have a set of fingerprints for potential intrusions. And these fingerprints or signatures are developed by security analysts only after they've isolated and studied certain threats. And the idea, your system then observes certain traffic patterns in your network, and if it finds a match to one or more of these signatures, it declares an intrusion. The advantage of these systems is that they offer a very low false positive rate. A false positive is where you actually mistakenly declare an intrusion, but there's no intrusion taking place in your network. They have very low false positive rates, these misuse detection systems, but typically they cannot detect previously unobserved attacks. And the reason for that is if you don't have a signature for the attack, it's like not having the virus definition for the virus that you're trying to find. You will not find it. A bit of a more recent approach is that of anomaly detection. The idea here is to construct models of legitimate traffic patterns. So instead of looking at malicious traffic patterns, you're now defining a model for legitimate traffic. And then you observe traffic in your network, and any traffic pattern that deviates from these legitimate models are tagged as malicious. The big advantage of this approach is that you can detect certain previously unobserved attacks, specifically those attacks that cause disruption to your traffic patterns. But typically these systems exhibit high false positive rates. The reason for that is, of course, your model might not accurately reflect what's really happening in your network, but more importantly, your legitimate traffic or your anomalous traffic patterns might not necessarily correspond to an intrusion. It might just be that it's some unusual usage scenario in your network. So we've been focusing on our research more on the anomaly detection approach because of its ability to detect these previously unknown or emerging threats. There are, in general, two ways of doing anomaly detection. We've got what we call statistical techniques and machine learning techniques. In your statistical techniques, you usually have some statistical model that describes your legitimate traffic. You can have a univariate or multivariate distribution, and if you for a certain feature, that might be indicative of an attack. And if you see outliers, if you see values that fall within the tail of your distribution, for instance, you will declare malicious activity or the fact that an intrusion is taking place. Another approach for statistical techniques would be to do time series detection. Over here you have a ticker graph of some feature. So this is where we plot a certain feature over time. And then if we see sudden changes or rises in activity on this ticker graph, we can say, but this is perhaps an intrusion taking place. The way this is done, one usually filters your ticker graph to remove high frequency noise and then does some form of thresholding where you declare a certain level. And if you see any observed traffic beyond that level, you declare an intrusion. Machine learning techniques are a bit different. You get supervised and unsupervised machine learning techniques which have been successfully applied to network intrusion detection. In supervised learning techniques, you use a pattern recognition algorithm, something like a support vector machine or a neural network, to learn some model of legitimate traffic. And using this model, one can then do anomaly detection by comparing observed traffic to it. The other technique, well, before I move to that, maybe I can just say with supervised learning, one requires labeled data. One requires a test set of data which one has previously classified as either being benign or malicious in order for these techniques to train and to memorize these patterns that they see in the data. With unsupervised learning, the situation is different. You typically do not have labeled data. And the idea here is to use techniques which learn or try to adapt to hidden structures in your data. So it attempts to find patterns in your data as well and use this, these hidden patterns as a model for intrusions. One compares then again the observed traffic against the model. So if it doesn't match, then it's an intrusion. So moving on, statistical techniques and machine learning techniques both have their advantages and disadvantages. Probably the greatest advantage of statistical techniques are that they're real time. It's critical to provide real-time protection in your networks. One cannot only learn about an intrusion a few hours after it's occurred. Because your information might have been stolen already. Statistical techniques are also adaptive and they have online model construction, which means you don't have to stop and recreate a model every time you want to update your model. You can keep on doing detection in real time. The disadvantage is that statistical techniques can potentially be trained by an attacker. If an attacker inserts malicious traffic patterns while you are building your model of legitimate traffic, you'll be mistaking legitimate traffic for anomalous traffic, or at least the other way around. So this is a big problem. We also have the rapid detection capability, but this implies more false positives. So typically, because you're doing it with this in this real-time fashion, it tends to exhibit much more false positives than your machine learning techniques. The machine learning techniques are able to detect more intricate attacks. That's their greatest advantage because they're able to model these subtle relationships that you see in the data or memorize these subtle patterns that might emerge. The problem is their practicality. They have a very heavy data pre-processing burden. And they also require labeled data in some cases. And we're only now really starting to see the emergence of machine learning techniques being used in real technology. Up in the past, it's always been statistical techniques. So this brings me now to the research and development work we are doing at the CSIR. So in my group, we are doing 3 areas key research. We are doing research mostly in anomaly detection, but statistical time series-based detectors is our one research area. Second is unsupervised machine learning-based detectors. And then finally, we have also developed a network intrusion detection software platform that we can use to detect intrusions in computer networks. So I'll maybe give an overview of each of these. For our statistical time series-based detectors, as I mentioned previously, the key drawback that limits the practicality of these systems is the false positives. If your machine or your intrusion detection system triggers false positives at a constant rate, you're going to disable it and it's useless. So we are looking at ways of suppressing false positives in these systems. 2 approaches would be to have a 2-stage detection approach, which I will be talking about throughout the rest of the presentation, so I'm not going to focus on it now. The multi-resolution detection approach, this is where we build models of legitimate traffic and where these models span multiple time frames. The idea is we want to capture cyclic trends that might be present in our data in these models. So for instance, let me give an example. You will probably see a significant spike of network traffic around about 7 o'clock or 8 o'clock in the morning. And this is due to people arriving at work and booting up their PCs. Does this mean it's an intrusion? No, it's just people arriving at work. So if we are able to capture that trend, that cyclic trend in our model for intrusion detection, we don't have to declare a false positive or a detection every morning at 7 o'clock. So our multi-resolution detection technique is also a way to suppress false positives. Then in unsupervised machine learning-based detectors, now these, many examples of these exist in the literature, but typically these works perform some kind of feature selection in their detection chain. The reason for this is to improve your classification rate by throwing away some features that might be irrelevant for the purpose of doing intrusion detection. But to the best of our knowledge, all works up to date use labeled data. They're supervised techniques for doing feature selection. We've developed a new unsupervised technique for doing feature selection. In other words, it does not require labeled data. And this is very important because labeled data is not available in practical networks. And we've shown that our unsupervised feature selection technique is able to match those techniques currently in the literature that require labeled data. And then finally, our own network intrusion detection software platform. This is a software system that you can deploy in your network to do intrusion detection and warn you of threats. It provides several functionality, deployment and configuration of sensors and detectors throughout your network. It allows you to monitor your network traffic patterns to gain situational awareness of what's going on in your network. And it also allows you to do incident logging and post-mortem analysis. So if an intrusion does occur, you can actually learn something from it and see what type of intrusion it was. Okay, so I'll be focusing a little bit more on time series detection techniques throughout the rest of my presentation. And maybe before we get into the details, I give here an example of a time series detection problem. So on the x-axis, we have time. On the y-axis, we have some feature that we observe in our network. This might be, for instance, the number of requests to a certain web server. And what we want to do is we want to detect abrupt changes in this graph, this blue graph that I've drawn here, which might signify an attack. So in this instance, I've inserted an artificial attack at around 85 seconds, or 85 minutes. And you can see there's a significant jump in the requests to your web server that occurs due to this attack. And we want to, as quickly as possible, detect that point in time where we see this rise in activity. So the way we do this is we compute what is called a moving average, which is the solid red line that you see there. This is an average that is indicative of at a certain window in time, what is our average for that process at that point in time. And then we define a certain threshold, which is a certain level above our moving average. And we declare anything that is above that threshold to be an intrusion. The problem with this approach is that, if you can see here, there's no attack present at this point in time, yet you see threshold crossings. You see that your blue line has crossed this dashed line, which represents our threshold. And this is a false positive because there's no real malicious activity yet happening in our network. And then after 85 minutes, you can see the sudden rise, and here are some threshold crossings as well, the green triangles. But these are true positives because they correspond to actual intrusive activity that's happening in your network. What we want to do is we want to maximize the true positives and minimize the false positives in our detector. And these false positives cause a significant problem to current systems. So we have proposed a two-stage detector for suppressing these false positives. In the first stage, we do conventional time series detection, as I've shown on the previous slide. And then in the second stage, we do a finer-grained analysis. This means we look in greater detail at what's happening in your network, in your time series, to try and determine if the threshold crossing that you've seen is really an attack or not. So the second stage, as I've mentioned, performs a finer grain detection to suppress false positives. And the second stage algorithm triggers only upon a threshold crossing in the first stage. The reason for this is because you're doing a more detailed analysis, your algorithms are computationally more complex. You may not necessarily be able to run them in real time. So only if your first stage triggers an alarm do you actually look at a finer grained analysis and go in deeper. There are many different potential algorithms one can use for a second stage detector. One would be a spectral based detector where we look at the different frequency components of your signal to see maybe you observe irregular periodicity, which may be indicative of an attack. That's one potential approach we're investigating, but for now we have already investigated what we call the inter-arrival time detector. And what we do with the inter-arrival time detector is we actually look at the time lapses between requests to your web server, or in general in your metric. It's the time difference basically between requests. And it's been shown in previous works that this distribution of these inter-arrival times can change quite abruptly if an attack is present in your network, if you maybe again see some periodic activity. And it is this inter-arrival time detector that we've developed and experimented with at the CSIR. So this is a block diagram that illustrates our second stage of detection. Before we get to the block diagram, maybe I can explain it on the hand of these figures I have here. At the bottom left, I've given a time series with a series of threshold crossings. Now we want to perform a detailed analysis to determine whether these threshold crossings are really part of an attack or not. The way we do this is we divide our time axis into two windows. We have a left and a right window illustrated here in red and blue. And what we do is we try to estimate the distribution of our inter-arrival times within these two windows. If we see that the distributions, the density functions, are significantly different between these two windows, it is likely that an attack is taking place because you see an abrupt change in your inter-arrival time. So what our system does is we calculate a kernel density estimate of the inter-arrival times in the left window and in the right window, and then we calculate a divergence metric. So here is an example of two distributions. The red curve corresponds to the left window and the right curve because you see a little bit of an increase. You now see a bump over here. We want to associate a number with the degree of similarity or dissimilarity in our case between these two curves, and we call that a divergence metric. So that metric is a number. The bigger the number, the more dissimilar these two curves are. And then we apply a threshold to this number after we've calculated now. And if it's above a certain threshold, we declare that indeed there is an attack taking place. Okay, we did some experimental work. We've applied this technique to the detection of denial of service attacks against a web server. It's a corporate network with compromised workstations. The attacker has already compromised the network. He's now using some of the internal nodes to flood the web server in this network with attacks, denying legitimate users access to the website. This is a ticker graph of what the normal activity, this is legitimate activity, looks like to the web server. What we did was we superimposed certain attacks on top of this activity to see how well our detector can actually pick it up. This is a diagram of the network that we haven't simulated this ourselves. This is a data set that's available on the internet. And the red line here illustrates the flow of packets from our compromised host to the web server. And our IDS system, intrusion detection system, sits here and it's listening for traffic, trying to spot these patterns. This is my second last slide. This is just the setup of our experimental work. For our first stage algorithm, we used the exponentially weighted moving average filter with a ticker period of 2 seconds. So every tick corresponds to 2 seconds worth of data. For density estimation, we used the Gaussian kernel density estimation technique with Silverman's heuristic over the log of request interval times. If there are any questions on this afterwards, please feel free to ask me. For the divergence, we used a symmetric Kullback-Leibler divergence, which is given by this equation down here. It involves integrals over these densities we've calculated in our previous step. And our window length is as well 31 requests. So we have 30 inter-arrival times in each window. And this is our results. So the results is this figure illustrates the true positive percentage as a function of the false positive percentage. So for good results, you would want to lie as far as possible to the top left of this graph, because it means you've got very low false positives and high true positives. Now these curves here illustrate different setups of our experiment. The blue curves, this is where we've superimposed an attack on the data which is 100% as large. So it's exactly as large as your ambient traffic level. The red curves, we inserted a larger attack. So your traffic, the attack packets that we insert is at a level 150% larger than your ambient traffic level. And so what we will do is we will compare blue curves with blue curves and red curves with red curves. So the squares indicate where we only do one stage detection. So this is our baseline, our traditional technique for doing intrusion detection, whereas our circles indicate where we now do the two-stage detection. And as you can see, where we do the two-stage detection, there is indeed a significant decrease in false positives. For the 100%, the blue curves, we see between 15 and 20% decrease in false positive rates. When your attack is more prominent, the gains are even larger. In some cases, up to 30 and 40% reduction in false positives. So the reason we are pursuing this is if you can reduce the false positives, your systems become more practical. And that is why we're considering this work. Thank you.